Up to this point, we've discussed moments due to forces. That is, there has always been a force present in order to have a moment. This raises a question. Is it possible to have a moment present without a force? In a way, there is. It is possible to have a moment without a net force. This illustration from our introduction of the moment shows how this is possible. Instead of applying a force to a single wrench, a worker now grips the pipe with two different wrenches on either side of the pipe. He pushes down on one side and pulls up with an equal and opposite force on the other. As a reminder, this combination of bending and twisting is what happens when a worker applied a force through a single wrench. When the worker applies forces that are equal and opposite on either side of the pipe, it tends to be a much more pure twisting kind of moment. In this particular illustration, the jaws are separated by some distance along the axis of the pipe, so there actually would be a little bending involved in this particular application as well, but it's mostly just a twisting moment. Two equal and opposite forces whose lines of action are separated by some distance constitute a special force system called a couple or force couple. Because the forces are equal and opposite, there is no net force. The separation of the forces' lines of action results in a net moment, or a pure rotational load. Although you probably haven't recognized it as such, you often apply couples. Suppose you stop at a convenience store between classes and get a soft drink. It has a twist-off cap. You hold the bottle in one hand, grip the cap between thumb and forefinger with the other, and then squeeze and twist to get the cap off. The squeezing results in a normal force on either side of the cap. These are equal and opposite forces, but are not a couple because their lines of action are coincident. A significant squeezing force is necessary because the largest friction force you can exert is proportional to the normal force. The friction forces are tangent to the bottle cap and equal and opposite as you move your thumb and forefinger in opposite directions during the twist-off. These friction forces constitute a couple, equal and opposite forces whose lines of action in this case are separated by the diameter of the bottle cap. This slide shows two different graphical representations of couples. On the left, the forces are shown as vectors, and one force is the negative of the other. On the right, the scalar magnitudes of the forces are shown on vectors going in opposite directions. As with our other calculations, there will be a vector approach and a scalar approach for calculating resultant moments, and you may see either one of these representations depending on the approach we're taking. Using the vector approach, the moment of a couple is shown here as the cross product between a relative position vector and one of the force vectors. We'll be able to prove the form of this shortly. The important point is that the relative position vector starts somewhere on the line of action of one force and ends somewhere on the line of action of its companion force. And as with so many other similar calculations that we've been doing, we have flexibility to decide where to start on one force and where to end on the other force. Alternatively, we could use the scalar approach as long as we can identify the moment arm d, the perpendicular distance between the force's lines of action. As with calculations discussed in the previous two sections, the scalar approach is most easily used in 2D problems or in relatively simple 3D problems where such a perpendicular distance is easily defined. Also, as in previous discussions of the scalar approach, this expression just gives us the magnitude of the force couple. To get its direction, we still have to use the right-hand rule, and our approach will be consistent with what we showed on the previous slide using the vector approach. So I could imagine being on this line of action and looking towards the companion force, and I'll just draw the position vector here so I can more easily take the cross product of r into f. That's going to have a direction that's consistent with the moment that's shown in the figure. Alternatively, I could come over to the line of action on the other side and look towards this force. Again, I'll put the position vector over here and cross that into f Either one of these is consistent with the direction of the moment that's shown in this figure. A force couple applied to a body has an important characteristic. It has the same influence on every part of the body. To see this, we calculate the net moment about an arbitrary point C on a body. Making use of the relationship between the relative position vectors, we see that the end result contains no information about the location of C. We could repeat this exercise for any number of points on or off the body and get the same result. Alternatively, we could hold our position fixed and move the force couple anywhere around in space and get the same result. The moment of a force couple is sometimes called a free vector, in that it can be picked up and placed anywhere on a body without changing the nature of its effect on the body. Note that this is different from the latitude permitted with an individual force vector. We said previously that we were permitted to slide a force anywhere along its line of action, but we couldn't pick the force up and place it on a different line of action without changing the nature of the force's influence on the body. Force couples are not so constrained. We have the freedom to place them anywhere we like without changing the nature of the load on the body. We will use the phrase equivalent force system to describe two or more different force systems that have the same influence on a body. In this illustration, we have a block of undetermined thickness that is 2a by a in the x and y directions respectively. In figure A, we have equal and opposite forces in x whose lines of action are separated by distance a. This produces a moment of magnitude Fa, and the right-hand rule tells us that the direction of the moment is in the plus z direction. Again, we could get this by positioning ourselves on the line of action of one of these forces looking towards the other. Here's the position vector r. I cross that into F, and I'm going to end up with a moment whose orientation is in the plus z direction. In figure B, we have simply moved this same force couple to the top of the block. In figure C, we have a force couple whose lines of action are in the y direction, and these are separated by a distance 2a, so we reduce the force strength by half to produce a force couple of the same magnitude. And once again, I can start at this line of action, look towards this force, r crossed into F will again produce a result in the plus z direction. Finally, in figures D, E, and F, we have the resultant couples at three different locations on the top surface of the block. Any of the loads in A through F have the same influence on the body. It should be mentioned that this claim of identical influence rests on the assumption that we can treat the body as rigid and not deformable. A force produces local deformation about the point of application. If we were able to see the deformation accompanying application of the load, we would see local deformation features about the bottom corners of figure A that would shift to the top corners in figure B. We would similarly see other local deformations at points of application of load in the other figures. Leaving these local features aside, the effect of the loads on the bulk behavior of the body would be identical for all 6 load cases shown. We now consider 3 examples involving calculation of moments due to force couples and equivalent couple representations. In our first example, we consider a number of ways to apply a pure moment load to a bracket. In cases A, D, and E, force couples are applied in different ways. In cases B and C, a single moment is applied at different locations on a bracket. In part A, we're asked to determine P and alpha so that the forces are a couple, and then to determine the moment of that couple. Since the forces must be equal and opposite, we know that P is 20 newtons and that the angle alpha is the arctangent of 3/4 or 36.9 degrees. We can use either the vector or scalar approaches to find the moment of the force couple. As this is a 2D problem, the scalar approach will be feasible, but one small adjustment will help us get the answer more quickly. Instead of analyzing the force couple as is, we'll break it into a force couple in X and a separate force couple in Y. So we'll decompose these forces into X components and Y components, and you'll notice that we're decomposing these tail to tail so that the lines of action of the individual components intersect the original line of action of the unresolved force. Given the 3, 4, 5 triangle, we can see that each 20 Newton force can be resolved into a 12 Newton component in X and a 16 Newton component in Y. We can also see from the right-hand rule that both component couples are exerting counterclockwise moments. The result is that M is equal to 12 centimeters times 12 newtons plus 8 centimeters times 16 newtons, and the result is 272 Newton centimeters. In parts B and C, we're asked to determine moments MA and MC so that the loading is equivalent to part A. This is as simple as MA equals MC equals 272 Newton centimeters counterclockwise. In parts D and E, we're asked to determine equal and opposite pairs, F1 and F2, and then Q1 and Q2, that produce loading equivalent to part A. Although not represented explicitly in the figures, the intention is that the lines of action of the forces in both cases are perpendicular to the levers shown. The perpendicular distance between lines of action is just the sum of those lever lengths, so we end up with F1 equals F2 equals 272 Newton centimeters over 22 centimeters, which is 12.36 newtons. And Q1 equals Q2 equals 272 Newton centimeters divided by 18 centimeters, which is equal to 15.11 newtons. Note the fact that one of the levers is inclined at 20 degrees from vertical and the other at 10 degrees from vertical is irrelevant, as is the fact that one pair of forces is equidistant from the fastener at C while the other pair is at different distances. In this second example, a cable is configured through rings at B and C in such a way as to apply a twisting load to the end of the plate. The specification that the rings are frictionless is a way of telling us that the tension in the cord is uniform. The problem begins by asking us to specify dimensions A and B so that the forces are aligned equal and opposite and so constitute a couple. The second part asks us to then determine the moment of that couple. The dimensions A and B have to be selected so that RAB and RCD are parallel. We can see that A and B are separated in Z by 18 inches. C and D are likewise separated in Z by 18 inches. This tells us the separation between C and D in X and Y should be the same as the separation between A and B in X and Y. In looking at the dimensions given in the figure, this tells us that A is 15 inches and B is 24 inches. The next decision is whether we should use the scalar approach or the vector approach to find the force couple. Because of the general 3D orientation of the forces in the problem coordinate system, I would suggest the 3D approach. Either of the following will work. We could write the moment as RCB crossed into the tension on the unit vector that points from B to A, or we could write RBC crossed into the tension on the unit vector that points from C to D. From the figure, we have that RBA is equal to minus 12I minus 4J plus 18K inches. The magnitude of RBA is 22 inches, and the unit vector then is RBA divided by its own magnitude, which is minus 6/11 in I, minus 2/11 in J, and plus 9/11 in K. The moment is then 9I inches crossed into 200 pounds on this unit vector UBA. Only the second and third terms survive, so we have 1,800 inch-pounds on minus 2/11 I cross J plus 9/11 I cross K. I cross J is plus K, and I cross K is minus J, and the net result is minus 1473 J minus 327.3 K inch-pounds. Finally, in our last example, we consider a satellite using positioning thrusters to perform attitude adjustments. The problem states that thrusters are fired in pairs so as to produce couples. The pure moment loads from these thruster pairs will cause the satellite to rotate into a new orientation. As an aside, many of you will learn in a fluid mechanics course that thrust, which is a force, is determined from the product of mass flow rate and flow velocity. So we get a thrust, which is a force, can be written as a mass flow rate times or on a velocity vector. We might note that the units of this problem will in fact give us a force because m dot is going to have units of, for instance, kilograms per second, and the units of velocity will be meters per second. And you can see that the product of those two things will give you kilogram meter per second squared, which is in fact newtons. Again, vector t is thrust, not tension. Scalar m dot is the mass flow rate of the expelled fluid, and vector v is the expelled fluid's velocity. We are told in the problem statement that each of the thrusters exerts a 3 Newton force, and we want to find the resultant moment from the two pairs of thrusters. Even though this is a 3D problem, the thruster orientation in the coordinate system given is sufficiently simple that we could use either a scalar approach or a vector approach to get the resultant moment. Consider first the AC thruster pair. This pair lies in the YZ plane and exerts forces in the Z direction. The perpendicular distance between lines of action is 1.2 meters. The right-hand rule can be used to give us the direction of the force couple, and that's going to be in the plus x direction. So using the scalar approach, we can say that the moment due to the AC thruster pair is 3 newtons times 1.2 meter in the plus I direction, or 3.6 I Newton meters. The BD thruster pair also lies in the YZ plane, but these thrusters exert forces in the x direction. The perpendicular distance between these lines of action is also evident from the figure. The slope in the YZ plane forms a 3, 4, 5 triangle, and the distance between forces is 2 meters. The right-hand rule gives us the orientation of the moment from this force couple as having a positive y and a negative z component. It's a little bit difficult to see here because of the perspective view. From this perspective, this force looks like it's almost parallel to the position vector from D towards B, but keep in mind that that position vector is in the YZ plane, and the 3 Newton force at B is in the plus x direction. If we do that cross of that position vector into that force, it's going to give us a moment that points in this direction and will be perpendicular to that position vector BD in the YZ plane. The result of this is that the moment from the thruster pair BD will be 3 newtons times that distance between lines of action, which is 2 meters, so it's 6 Newton meters, and it's on a unit vector that is 4/5 J minus 3/5 K, which gives us 4.8 J minus 3.6 K Newton meters. The resultant moment is just the sum of these two contributions, and that ends up being 3.6 I plus 4.8 J minus 3.6 K Newton meters.